Okay, maybe we can start. Person.
All right, yeah. So welcome everyone to the session 7 of APPROX. Today we have 4 great talks. For our first talk, we have the paper Low Rank Binary Matrix Approximation in the column subnorm. This is a paper by Fedor Fomin, Peter Golovak, Fahad Panolan, and Kirill Simonov. And today Fahad will be giving the talk.
Thank you, Person, for introduction. Okay, I will be talking about low rank binary matrix approximation in column subnorm. As mentioned, it's a joint work with Fedor, Peter, and Kirill. Okay, so low rank matrix approximation is a method of compressing matrix by reducing its dimension. It is widely used in data analysis, for example, principal component analysis. It has application in machine learning, data mining, scientific computing, etc. So in general, what is the problem? Low rank matrix approximation. We are given a matrix A, say m times n, the order is m times n. And we are also given a positive integer r. And our objective is to find a low rank matrix B. That means the rank of B should be at most r. And minimizing some matrix norm of A minus B. Two widely used norms are like Frobenius norm, and the another is spectral norm. Okay. Frobenius norm, it's kind of an averaging measure. On the other hand, the spectral norm gives something like a worst case stretch of a column. So the spectral norm is defined like this. Okay, so you can just read it. Okay. And both these problems are solvable in polynomial time using singular value decomposition. And we study mainly like the second analog in the case of binary matrices, and we consider matrix operations over GF2, so over finite field, and more specifically binary matrices. So what is low rank matrix approximation over GF2? As I mentioned before, we are given a matrix A, and we are also given an integer R. And our objective is to find out a matrix B of low rank R, which means that B can be written as C times D. And where the number of columns in C is at most R, and the number of rows is at most D. And in the case of matrix approximation over GF2, this product is over GF2. Okay. And the objective is to find a B is equal to C times D, such that some norm of A minus B is minimized. Okay. Two most popular one you can think of is entry-wise L0 norm of A minus B. That means the number of entries mismatch between A and B. Okay. And another one you can, so that could be somewhat analogous to the Frobenius norm in the case of reals. Okay. And something analogous to spectral norm could be column sum norm, where what we want to find out is then I want to minimize the maximum number of ones in a column of A minus B. Okay. Maximum number of ones in a column of A minus B. So here it is, in the case of entry-wise L0 norm, maximum number of mismatches. And in the case of column sum norm, the number of mismatches between A and B. And in the case of column sum norm, the number of mismatches between columns of A and B. Like you pick jth column and then jth column, like how many entries are mismatching. So you want to minimize maximum over J of this quantity. So this is the problem mainly we consider, that we call it L1 rank R approximation over GF2. The other problem, entry-wise L0 norm, we call it low GF2 rank approximation. Okay. So in the first case, this is something like an averaging measure, and in the second case, it is a worst case stretch over a column. Okay. So what is known about the low rank approximation? That means I want to minimize the Hamming distance between A and B, where B is the matrix I want to compute. And the problem is NP-hard. It is shown independently by two sets of authors. And there is a p-task running in the time mentioned in the slide. And there is also a randomized linear time approximation scheme. That is, running time is f of k comma epsilon times, k equal to 2 to the r. Okay, sorry for mistake. K equal to 2 to the r. N times m. N times m is the size of the input. And this is also achieved by two set of different authors. Okay. And what we consider here is L1 rank R approximation over GF2. That is, we want to minimize the column sum now. Or in otherwise, the number of the maximum number of ones in a column of A minus B, the matrix A minus B. And a simple reduction from closest string shows that the problem is NP hard. And the main result in this paper is there is a p-task for this problem. The running time of it is m to the power order 1, n to the power order of some function of r and epsilon. For r is equal to constant, it is a p-task. Okay. So this is the main result in the paper. Okay. And so I just summarize the result here. And if there is a couple of minutes, I will just give you like proof outline. So we proved like p-task for the problem. And naturally one can ask, can we get an algorithm of running time f of epsilon into m times n to the power some function of g of r, or can we remove epsilon from the exponent? And a simple adaptation of a result about closest string by Saigon et al., we can show that that's not possible even for r equal to 1. Okay, assuming fpt not equal to w1. And in fact, assuming exponential time hypothesis, one can show that even I cannot get a running time of the form f of epsilon into n to the little of 1 by epsilon, even for r equal to 1. Okay, so that kind of a strong hardness result we can get it by adapting the proof what is already known for closest string. But the open question here is, can we get an algorithm of running time f of r comma epsilon n mn to the power poly in 1 by epsilon? Or in other words, can we remove the r from the exponent and make it as a separate function, f of r comma epsilon? So I know that epsilon cannot be removed. So now can we remove r from the epsilon? That is an open question here. Okay. And do I have time? I don't think, right? Do I have 2 minutes time?
Yeah, I think you can take 1 or 2 more minutes, or we can take some question, whatever you like more.
Oh, okay. Then maybe like I will show you one more slide and then I will stop. Yeah. Okay. So the proof sketch is like proof outline is like it has 3 steps. One is I just reduce my problem, that is matrix factorization, to something like a k-center problem, and then using dimension reduction technique, a different version of k-center problem that is called a binary constrained partition center. And then later at the end, we use integer linear programming and randomized rounding technique to solve binary constrained partition center. So here we need, so from for this reduction from here to here, we need to use dimension reduction technique. So we will have some loss there. And here we approximately solve in the step 3 using integer linear program. So maybe like the other slide, it may take more time, so I will skip that. Okay, how this problem is defined. Okay, and so okay, so this is a problem which is closely related to k-center problem, and we can reduce to that kind of a k-center problem, and where k is equal to 2 to the r, where there is some relation between the center vectors. And then at the end, what we do is integer linear programming, and then solve it using using integer linear programming and randomized rounding technique. And if you have any more questions, I will take it.
All right, thank you, Fahad. I think maybe we can take a very quick question, one very quick question in case anyone has it. I have a quick question. So if we don't want a p-task, but we are okay with some large approximation, can you get a much faster algorithm?
Okay, I have not tried about that question. Like say probably like some order 1 approximation.
Yeah.
Where I believe that could be possible.
I see.
Because this problem is closely related to closest string, and I think you could get a constant factor in poly n for closest string, right? A factor 2.
Yeah, I think so too.
Yeah. So at the last step, it is related to that. But in the second step, it is related to dimension reduction. There is also like we do have like this kind of n to the power, function of 1 by epsilon. But I don't know currently whether we can remove that. So,
I see.
Yeah, it's a nice question to try.
Okay. Yeah. Thank you so much, Fahad. And maybe I think we should start the next talk.
Okay. Thank you. I will stop sharing.
Thank you. So for the next talk, we have the paper Maximizing the Correlation, Extending Grothendieck's Inequality to Large Domains. And this is a paper by Dor Kaselnik and Roy Schwartz. And today Dor will be giving the talk. No, I cannot hear you. Can everyone else hear Dor?
No.
I cannot hear.
No.
Okay, let's see.
Roy is muted, I think.
Is Dor presenting or is Roy presenting?
Can you hear me? Can you hear me now?
Now
Yes, we can hear you now.
Okay, I think I was on mute. So this is a presentation about maximizing the correlation, extending Grothendieck's inequality to large domains, and this is a joint work with Roy Schwartz. Okay, so in the model of correlation clustering, which is basically a family of graph problems, we're given a graph, an undirected graph, where the edges are labeled by a plus or a minus sign. A plus sign indicates that the nodes are similar, and the minus sign indicates that the nodes are dissimilar. And the goal is to find the clustering, that is a partition of the nodes in the graph, in such a way that similar nodes will be together in the same cluster, and dissimilar nodes will be apart. They will be in different clusters. So we want to find the clustering that agrees the most with the labels of the edges. Okay, so let's see an example. Here we have a graph where the edges are labeled by a plus sign or a minus sign, and we maybe have also a weight function for the edges. And here is an example. Here is a clustering of the graph. We have here 4 clusters, and some of the plus edges reside within the cluster. Some of the plus edges cross between clusters, and so for the minus edges. Now we can ask how good a clustering is. How can we measure how good the clustering is? So the first thing we can measure are the agreements. What are the agreements? These are edges that are classified correctly. For example, these are the plus edges that reside within clusters and minus edges that cross between clusters. So here you can see in bold the edges that are in agreement. The rest of the edges are classified incorrectly, and they're called the disagreements. So now when we have these two measurements, we can define the following objectives. So the first objective is called max agree, and the goal is to find a clustering that maximizes the number of agreements, or maximizing the sum of the weights of the agreements if you have weights on the edges. Okay. The second objective is mean disagree. And here the goal is to find a clustering that minimizes the number of disagreements. So these two objectives are very similar, but they are quite different if you want to approximate this problem. The third objective is called max score, and here we want to maximize the correlation. What is the correlation? The correlation is basically the difference between the number of agreements and the number of disagreements. So you sum up all the agreements, or all the weight of the agreements, and you subtract the weight of the disagreements, and this is the correlation. So you want to maximize this value. So basically, you want to simultaneously maximize the agreements and minimize the disagreement. Okay. So in previous works, there were many works on correlation clustering, and specifically for max score, it was first introduced by Banzal et al. And Sharika and Wirtz presented an omega of 1 over log n approximation when the input graph is some general graph. Okay, and in our work, we studied this objective. We studied max score, where the input graph is a bipartite graph. And we also extended it to a problem called max k-core, where we limit the number of the clusters in the output to be at most k, where k is some constant. And what we do is present approximation algorithms for these problems, and we show how these problems relate to Grothendieck's inequality. Okay, so our results, the first result is that there is a polynomial time approximation algorithm that achieves a factor of 0.254 for max score on bipartite graphs. And the second result is like sort of an extension of the first result, is that we can approximate max k-core with the following guarantee. And we can see that as k goes bigger, the approximation factor will decrease. And for arbitrarily large k, we get the guarantee of the first results. And in addition, these results are also natural extension of Grothendieck's inequality to large domains. I will not talk about this specifically, but you can read about this in our paper. And a short slide about the technique. We are basically suggesting a natural SDP relaxation for this problem for max score. And then we show how to run the solution of the program by extending Krivin's method to allow more than 2 clusters in the output. And then we show how to adapt this relaxation and the rounding algorithm for the max k-core problem, where the number of clusters in the output is limited. Okay, so this is it. Thank you.
All right, thank you, Dor, so much for the talk. Maybe we can take one question here.
Can I ask one?
Yeah.
Oh yeah, please go ahead.
Can you get some lower bound, like for your version, like is APPROX hard or something like that?
We don't have any hardness results. I don't know of any. We did show some bounds on the integrality gap of the relaxation, but these are not hardness results. So I don't know of any.
Okay, thank you.
Okay.
Okay, let's thank Dor again.
Thank you.
Next, we have the paper on perturbation resilience of non-uniform K-center. This is a paper by Shayan Banyapayan, and Shayan will be giving the talk.
Can you hear me now?
Yes.
Okay. Hello, everyone. In this work, we study the non-uniform K-center problem, which is a geometric clustering problem. In this problem, we are given a set of points in some metric space. And the goal is to partition the points into K groups or clusters such that each cluster contains similar points. And here the notion of similarity is captured by balls. That means each cluster must be contained totally inside a ball in the metric space. So let me formally define this problem. So in this problem, we are also given K integers R1 up to Rk, which are also called the radii parameters. And the goal is to find K balls of radii alpha R1, alpha R2 up to alpha Rk, such that the union of these balls contains all the points, and the value alpha or the scaling factor must be minimized. And once we select the balls, the clusters are formed in a very natural way. You can assign each point arbitrarily to a ball that contains it, and that induces a partition of the points. And in this example, I have shown 5 clusters by 5 different colors. So you might have already noticed that NUKC is a natural generalization of the classic K-center clustering problem where all the radii have the same values. And this version is called the one radius class version of NUKC. However, in many applications, we need to consider non-uniform radii to exactly retrieve the underlying clustering of the data set. And in this example, I have shown, in this figure, I have shown such an example. Let me talk about some previous works of this problem. In the special case of K-center, 2 approximation algorithms are known. And these are all classical results. This 2 approximation factor is also tight. The general version NUKC was formulated very recently by Chakravarti et al. And they showed that this problem is hard to approximate within any fractal lambda. And they also obtained a constant bicriteria approximation where instead of K balls, you select a constant times K balls. And they also study the 2 radii class version of this problem where the parameters, radii parameters belong to a set of 2 values, R and R prime. So they can basically take 2 distinct values. And for this version, they obtained a true constant approximation. And however, even for 3 radii class version, no approximation is known. In this work, we study the NUKC problem under perturbation resilience. And this is a notion of stability which was introduced by Billu and Lenial in the context of the maximum cut problem. In case of clustering, an instance is called psi perturbation resilient if for some positive real number psi, if there is a unique optimal clustering for the instance. And if we increase or decrease the distances by a factor of psi, a multiplicative factor of psi, then the optimal does not get changed. And in the perturbation resilient version of a clustering problem, we assume that all the input instances satisfy this perturbation resilience property for some psi. And there is a rich literature of perturbation resilient clustering. For example, for K-center, under 2pr, we know that this problem can be solved in polynomial time. And this is a tight bound. This 2-factor is tight. And one can obtain this polynomial time algorithm even for the general case of asymmetric case center, where the distances are not necessarily symmetric. And note that this problem is, the general version of this problem is hard to approximate within any constant factor. And similar polynomial time algorithms can be obtained for many other clustering problems, including case center with outliers, which is also a special case of non-uniform case center. So in this work, we showed that NUKC under 2pr can be solved in polynomial time if we have a constant number of radii classes. And we show this by showing a reduction from this version of the problem to a firefighter's problem on trees with constant height. This constant is corresponding to the constant number of radii classes. And this version of firefighters can be solved in polynomial time. So we also obtain a polynomial time algorithm for our version. And for NUKC, the general version of NUKC, we showed that the perturbation resilience doesn't help, in the sense that for any gamma and psi, the problem under psi pr is hard to approximate within a factor of gamma. And this result is kind of surprising, because this shows that NUKC is one of a kind of the problems for which the complexity remains same even under perturbation resilience. And we show this hardness result by showing a chain of reductions. So here we need to show that in the instance of NUKC, we have a unique solution. So we start with a unique version of 3-set. And for the details, I would recommend the paper. So a few open questions. Is it possible to obtain a constant approximation for 3 radii classes? And also, it would be interesting to study parameterized complexity of this problem. And I conclude my talk with this, and you can ask if you have any questions. Thank you.
Thank you, Sayan, so much for the talk. I think we have a few minutes for questions, so please go ahead if you have.
I have a question. I'm Fahad. So is your problem on Euclidean plane or any metric? I could have missed it.
Our results is for any general metric space.
Okay.
Okay, so the polynomial time algorithm is for any general metric space, and even the hardness result we could show in Euclidean metric of 1 dimension.
I see. And the open question, it holds even in Euclidean plane. Am I right?
Yes, yes. It's even open in the Euclidean plane, like to obtain the constant approximation.
Okay. Thank you.
Yeah, sure.
So for parameterized complexity, which parameter are you thinking of?
A natural parameter would be K. Like in the clustering problems, like there have been some recent algorithms for other clustering problems where, yeah, they have used, like there are many problems for which you don't get constant approximation in polynomial time. But for example, for capacitated K median, and they showed that you can obtain a constant approximation in time FPT in K. Yeah.
All right. If there is no more question, then let's thank Shayan again.
Sure. Thank you.
For the last talk of this session, we have a tight 3/2 plus epsilon approximation for skewed strip packing. This is a paper by Galvez Waldo, Fabrizio Grandoni, Afus Jabal Ameli, Klaas Jansen, Arindam Klan, and Malin Rao. And Afruz will be giving the talk.
Okay, can you hear me now? Okay,
Yes.
thank you. Thanks for the introduction, Fasin. So let's begin. In the strip packing problem, as an input, we are given a strip with width W and infinite height. We assume that W is an integer. We are also given a set of n rectangles, which we call them items, each of which is associated with a width Wi and a height hi, which are integers. We also assume that Wi is less than or equal to W. And then the goal is to find a feasible packing, or shortly a packing of the items inside the strip, minimizing the height. Note that by packing, we mean a placement of the items inside the strip such that no two of the items overlap. Note that we are also not allowed to rotate the items. The state of the art of the problems, this problem is as follows. So strip packing is known to be 3/2 minus epsilon APPROX art. This can be shown by a simple reduction from the partition problem. Then there were a sequence of improvements in terms of approximation factor, started by a 3 approximation factor in 1980 to a 1.9396 approximation in 2009. And the current best known as a 5 plus epsilon approximation algorithm by Haren, Janssen, Pradel, and Van St. So now the open problem is this gap from 3/2 minus epsilon to the upper bound of 5 plus epsilon. A general approach of the previous results is as follows. So they start to classify the items according to their sizes. So consider mu and delta to be constant values in the range 0 to 1. Also assume that t is some upper bound on opt, which is less than 1 plus epsilon opt. Now we can classify the items by size. For instance, if both the height of the items is more than delta t and the width is more than delta w, we call the item large. If the height is more than delta t and the width is less than mu w, we call this vertical, and so on. An important observation here is that since we assume that delta is a constant, then there can be only constantly many large items. So basically this suggests as we can enumerate for having all the possible ways of packing these items. And this suggests that the hardness comes mostly from the rest of the items. Basically, if you are given an instant containing only large items, we are even able to compute the solution efficiently. So the solution, the question is that, is it also true for the complementary case? And by the complementary case, we mean an instance of strip packing such that for all the items, either Wi is less than delta W or Hi is less than delta T. We call this the delta skewed strip packing, which is basically the general strip packing discarding the large items. In this paper, we showed that this delta skewed strip packing is 3/2 minus epsilon APPROX hard. Then we presented a 3/2 plus epsilon approximation algorithm for this problem. So together with the hardness, we have an almost tight result. In the rest of the talk, I would explain some parts of the algorithm. So the general approach of the previous works are as follows. They start by transforming the optimal packing to a packing with simple structure. This is usually known as the structural lemma in the literature. This is done into 2 steps. So the first step is to partition the packing into constantly many rectangular sub-areas, which is usually called the containers. And then we try to shift and reorder the items so that they are packed inside the containers with a simple structure. So the algorithm would be as follows. So now that we have the structural lemma in hand, since the number of containers is constantly many, so you can iterate over all the structures to get the best structure possible. And then we try to place almost all the items using linear programming or dynamic programming inside the strip without going above the height of 1 plus epsilon opt. And note that by almost all, we mean a subset of items, including most of the items in terms of the area, so that the discarded items have only epsilon fraction of the total area. And since in the strip packing, we must pack all the items, then we need to introduce an extra container of height opt and with epsilon W for the unpacked items. Our strategy, however, is somehow different. So we basically place all the items with height larger than half opt inside the structure solution. This allows us to have the additional, this allows us to consider our additional container to be only of height at most 1/2 opt. We also have a new classification for the items. So for us, the first class of the items are the items of height at least 1/2 opt, which we call them the tall items. The second class is the class of the items which are of height from delta opt to 1/2 opt, which we call them vertical, and the rest of the items we call them short. So now I'm going to explain our structural lemma. So consider we have an optimal solution, and let opt be the height of this packing. So from this, we want to obtain a structure solution with height 3/2 plus O epsilon opt with the following properties. So the first property is that we show that we can place the tall items sorted according to their heights, and they are placed in the bottom left of the strip. For the short items, we show that if we allow a slicing of them horizontally so that they are sliced so that the slices have unit height, we can place them in the top right of the strip such that they form this decreasing profile. And then we shift the silhouettes of the tall items and this slices up such that they have constantly many jumps. And for this, we need to increase the height by epsilon factor. And finally, we can introduce the containers for the vertical items by drawing these imaginary lines from the corners of the silhouettes. And then we use this to pack the slices of the vertical items inside. Then we guarantee that after doing that, we still have this free area of width omega epsilon W and height opt half. So now the algorithm is basically try to find this structure by guessing, and then try to turn this fractional solution, and by fractional I mean since we allow the slicing, but originally we are not allowed to do that, to a packing of the original items. Note that when we do that, we lose a fraction of the items, but since we have this free area, now we can pack them inside this free area. And that is all. Thank you for your attention.
Thank you, Afruz, for the talk. I think we have a few minutes for the questions. All right, I guess if there's no question, let's thank Afruz again, and also thank all the speakers in this session. So there is about 20 minutes break between this and the next session. So see you in 20 minutes. Thank you.
Thank you. Thank you.